All right. Today we're talking about the tritone paradox and the non-commutative phase as creating time, space-time. So in science, there's the Fourier uncertainty, which is that I'll show it here. It's this right here. So it says that the frequency times the time has to be greater than or equal to 1/2. And so you can't simultaneously increase the resolution of both the time and the frequency. And this non-commutative phase actually, if you study Alain Connes or physicist B.G. Siddharth, who predicted the acceleration of the universe due to dark energy, and he should have got the Nobel Prize, but since he's Indian, he got discriminated against from India. And Basil J. Hiley, the collaborator with David Bohm, they all talk about how at zero time there is already non-locality as non-commutative phase. And this is what math professor Lou Kaufman calls primordial time. And normally I was corresponding with Dr. Ruth E. Kastner about this, and in science we use the photons for measurement and the speed of light as the invariant constant, and therefore we can create length from time directly now. And so the non-commutative phase is creating length, geometric space, from a primordial time that is before time frequency uncertainty. And so therefore it's also non-local as non-commutative phase. Now, if we look at the uncertainty principle again, the Fourier uncertainty, this 1/2. Okay, so we know that science has proven that humans can hear faster than the time frequency uncertainty principle, so we can achieve a resolution faster than the linear operator conversion. And why is that? It's because when we study the Pythagorean music theory, it's not based on an external instrument, or so that it's based on listening. So when we were reading Philolaus, and I pointed out recently, and somebody commented on, now they see what I'm saying about him flipping his lyre around, and I said that's the lyre of the lyre, because by flipping the lyre around, he's still within one octave, but he's able to then change what the quote-unquote bottom note is. So even though the bottom note is now it's the octave, so it's going in the reverse direction. But if you're listening to the root tonic, then you can't just reverse the direction of what the bottom note is, because it's not an external measurement. And so it's a diverging series of Pythagorean natural overtones and undertones. And this is why it's non-commutative phase, because if you did have the 1 as a 1-1 ratio, then the 3/2 as the undertone, the 3/2 wavelength and 2/3 frequency is a different pitch as non-commutative phase. So it's a C to F pitch, even though it's still a perfect fifth music interval. And so the number 3 is F as an undertone, but then as an overtone, it's 3/2 as C to G. And so that's 2/3 of the wavelength if you have a string that's 1. But if it's the undertone, then all of a sudden you need a 3/2 string, which is longer than the 1. And so you can either then flip the direction of your physical instrument around and then lie about what the root tonic is and say now it's going in the opposite direction of time and frequency. And then therefore you can create a new perfect fourth from what was 2/3 as the wavelength in the opposite direction of and then the common denominator is the 6 to 12 octave for 2, 3, and 4. So that's why they use the 6, 8, 9, 12. And so this is what Philolaus did, and Professor Richard McCurahan translated the Philolaus to discover what Andrew Barker could not discover, that Philolaus had flipped his lyre around to create the very first use of magnitude as an irrational number of ratios. So that's why the time frequency uncertainty is essentially a flipping of a physical phase as a angular frequency that in science is measured as radians with pi, with the circle. And so then when you use radians for frequency, then it's considered a unitless measurement, but it's not really unitless at all because it's dependent on an external physical measurement that's a linear operator. So therefore, the time and frequency measurement are inherently due to a change of the spatial measurement of time as a wavelength. Whereas if we measure time directly just as period, as an inverse of frequency, we can do it just through listening and therefore achieve a phase coherence of undertones and overtones at the same time to the one. And this is what I call the Hempel Hempel effect. And because visually you'll see a change if you shift the phase a quarter degree, then you see a change in the amplitude and the frequency. And so it looks like it should sound differently, but if you're listening to it, it's still a perfect fifth to the root tonic. So even though the pitch has changed, it's still the same interval. And so then this was proven in a roundabout way with the tritone paradox, where people, if they're not well trained in listening, they'll hear a change in the circular octave height as a visual height relative to the root tonic, as with the tritone, because the tritone is equally splits the octave, supposedly. But this proves that people have an inherent sense of absolute pitch based on the direction of which sound they hear first. And so then the next sound is heard as ascending or descending based on how much of a rotation it is relative to what they previously perceived as the root tonic. So if it's more than 6 steps of the scale, of a 12-note scale, then they perceive it as a counterclockwise rotation, and therefore it's descending. Whereas if it's less than 6 steps, it's perceived as ascending, even though it's a tritone, so you're not supposed to be able to tell the difference unless you have absolute pitch. And so that people are using absolute pitch inherently, and it's supposed to be this special skill. But if people are really listening to the source of the one as a 3-in-1 unity, that's noncommutative phase, and that's actually non-local awareness. That's before the creation of space-time.